It's been a year since Elon Musk unveiled the Cybertruck to the world, and over the past year we've learned a ton about the Cybertruck, and we will know more soon. But there's one area that's open to lots of speculation, and this is the efficiency of the Cybertruck and the size of its battery. There's been a few people who have looked into this, and in a past video I even hinted at some calculations that I've done. But you all wanted more, so it is time for some quick maths. Before we jump into this, let's define some terms that we'll be using a lot. First is force. I like to think of a force as a push or a pull on an object that is interacting with another object. This could be something like a gravitational force, which is the pull of a large object, like the Earth, on a small object, like me. It could also be something like the push of air on your hand as you hold it out the window of a moving car. So that's force, and if you apply a force over a distance, you get another quantity called work. A simple illustration of work is pushing a rock along the ground. To move the rock, you apply a push or a force, and when you multiply this by the distance that the rock has been pushed, you get the work that you've expended to move the rock. And intuitively, you'll know that the further you have to push the rock, the more energy you will have used. And this is why work is equivalent to energy. And they actually have the same units. Finally, let's define efficiency. Efficiency is the useful work done by a system divided by the energy input to the system. For a vehicle in the US, we typically measure efficiency as the miles that you can travel on a gallon of gasoline, and I'm told that in Europe it's typically defined as the liters of fuel that are used per 100 kilometers. So before we look at the Cybertruck, I'm going to take a look at my dinosaur burner, a 2017 Subaru Crosstrek. And I'm going to use this car to look at all the factors that go into calculating the efficiency of a vehicle. We know that all of the energy comes from the combustion of fuel inside the engine. And before being exploded, the fuel has a certain amount of energy in it, which I'm going to call EN. Both the combustion process and the drivetrain have energy losses. A large percent of the energy is lost as heat inside the engine, and then the rest is largely lost due to friction in the engine, the transmission, and really the rest of the drivetrain. Let's call the energy that's lost in the entire drivetrain EDT. The second energy loss a vehicle has to deal with is the rolling resistance between the tires and the road, and I'm going to call this ERR for energy rolling resistance. And then the final energy loss is due to the aerodynamic drag on the vehicle, and I'm just going to call this E-drag. So we have four energy terms: EN, EDT, ERR, and E-drag. And when we add up all four of these terms, we arrive at a big fat zero. Engineers call this equation an energy balance equation. Before we jump into the Cybertruck, I'm going to use the Crosstrek to illustrate how these energy terms and this energy balance equation works. First, let's look at EN. In the case of my Crosstrek, we just took a 1,907 mile round trip to Florida, or 3,069 kilometers. Okay, as an American, I hate to do this, but from here on out, the freedom units have to go. I mean, I'm okay with them, and I actually kind of love them in this weird, we're different sort of way. But the issue isn't so much that they can be really confusing when you're doing physics-based math, which they really are. The real issue is that I'm explaining physics-based math, and it's 10 times harder in English units. And I want this video to be as easy to understand as possible. Don't worry, I will put in the important bits in our units. So back to our 3,069 kilometer drive. During the trip, I filled up with gas 6 times. Each time I recorded the number of miles driven between the fill-ups, the fuel economy reported by the car, and the number of gallons needed to fill up the tank, along with the average speed that the car's computer read out. Now, there are some uncertainties in the calculated miles per gallon data reported by the car, and I'm not entirely confident in the car's prediction capabilities here, but I'm also not confident in the values that I calculated using the gallons used between the gas stations. The reason for that is that I stopped filling the tank when the pump auto shut off, and the pumps don't always auto shut off at the same fullness level. To minimize these uncertainties, I took the average of the car's values and my values. These values showed an average fuel economy of 7.48 liters per 100 kilometers at an average speed of 104.6 kilometers per hour. There's 31,802 kilojoules of energy contained in 1 liter of fuel. So multiplying our 7.48 liters per 100 kilometers by 31,802 kilojoules per liter, we get a value for EN of 237,879 kilojoules per 100 kilometers. Jumping back to our energy balance equation, we find that EDT is the next value that needs to be solved. Unfortunately, this is a super complicated variable to solve for because it not only includes combustion inefficiencies in the combustion process, but it also includes frictional losses in the engine, the transmission, and really the rest of the drivetrain. Then there are all sorts of auxiliary loads, which include like the air conditioner or the alternator, which would then run all the electronics and other systems. So rather than trying to piece this entire mess together, let's skip EDT for now. ERR results from deflection of the tire where it contacts the ground. As the tire hits the ground, it deflects from a circular shape to a flattened circular shape. And there's some energy that's required to bend the tire in this way. A portion of this energy is recovered when the tire springs back from the flattened shape, but there'll always be a portion of the energy that can't be recovered. And this energy is mainly lost as heat. We call this lost energy the rolling resistance loss. Rolling resistance is a factor of many different things, from the tire pressure, tire width, and even the temperature. Fortunately, engineers have come up with a simple method of calculating rolling resistance force, and this is to multiply the normal force of the vehicle by a rolling resistance coefficient, or the CRR. Now, normal force sounds all scary, but it really is just the mass of the car multiplied by the acceleration due to gravity. To convert the rolling resistance force to work or energy, we simply multiply by the distance that's been traveled. The rolling resistance coefficient depends on the type of tire, road surface, etc., making the calculation of a precise coefficient quite difficult. What we do know is that typical car tires fall somewhere between 0.01 and 0.015 when they're driving on smooth paved roads. But since we're doing quick maths, let's use an equation that I found. This equation attempts to correct the rolling resistance coefficient based on the tire pressure and the speed of the vehicle. Before our trip, I pumped up the Crosstrek tires to 2.6 bar. Plugging this into the equation along with our average speed of 104.6 kilometers per hour, we get our rolling resistance coefficient value of 0.013. With this in hand, we can finally solve for ERR. We know that the mass of the Crosstrek is 1,455 kilograms and the acceleration due to gravity is 9.81 meters per second squared. We multiply this by our distance of 100 kilometers and we get ERR of 18,556 kilojoules per 100 kilometers. Our final energy term is the aerodynamic drag. Like rolling resistance, calculating the aerodynamic force on a vehicle can be simplified by using a coefficient, which in this case is called a drag coefficient. To calculate the drag force, the drag coefficient is divided by 2 and then multiplied by the density of the air. Then this quantity is multiplied by the square of the speed and the frontal area of the vehicle. If we multiply this force by distance, we once again get the work or energy done by the aerodynamic drag, or in this case, E-drag. According to Subaru, the Crosstrek has a drag coefficient of 0.35, which lies right between a Ferrari F40 and the Tesla semi-truck. Although all these vehicles have virtually the same drag coefficient, it should be obvious that they will slip through the air very differently. And this is due to differences in their frontal area. A simple way of thinking about frontal area is that it is the 2D view you would get when you look at the front of the vehicle, straight on. This is why the Tesla Semi will have a greater drag force than an F40, even though they have a very similar drag coefficient. So, for our Crosstrek analysis, we need to find the 2D frontal area of the car, and to do this, I first measured the length of the grille, and then I took a picture of the car from front on. I used the grille dimension to scale the picture, and then I simply overlaid various rectangles and triangles to roughly match the frontal area of the car. I added up all the areas of the rectangles and triangles, and I was left with a frontal area of 2.06 square meters. Well, the final variables we need in the drag equation are the density of the air, which is 1.2 kilograms per cubic meter, and our speed of 104.6 kilometers per hour. Oh, and the 100 kilometers distance. Plugging everything in and correcting the units, we get 36,521 kilojoules per 100 kilometers. Now that we have EN, ERR, and E-drag, we know 3 of the unknowns in our energy balance equation for the Crosstrek. And using algebra, we can simply rearrange this equation to solve for EDT. Once we do this, we get a drivetrain energy loss of 182,802 kilojoules per 100 kilometers. Of all the energy terms, EDT is the most problematic, as it represents energy that's not being used to push the car forwards. When we look at the contributions of EDT, ERR, and E-drag, we see that about 77% of the energy in the fuel is lost during combustion or in the drivetrain, with only about 23% doing useful work to push the car forward. We'll call this 23% the fuel to wheels efficiency, But you didn't click on this video to see a Crosstrek. So let's see how these numbers play out for the Cybertruck. Well, we have the exact same energy balance for the Cybertruck, except that EN is now no longer the energy in the fuel, but the energy in the battery. So let's start with EN, or not. See, we don't know the energy usage of the Cybertruck, and that's pretty much why we're making this video. So how about EDT? This is a tough one too. We don't exactly know the drivetrain losses or the auxiliary power loads of the Cybertruck. But before we give up, let's try some educated guessing. Fortunately, Tesla has a few vehicles on the road already, many of which have an all-wheel drive drivetrain, which is very similar to that of the dual or the tri-motor Cybertruck. One of the best current data points for Model X efficiency was recorded by Bjorn Nyland in a 2019 Raven Model X. His highway test at 120 and 90 kilometers per hour revealed a drivetrain loss of approximately 13%, which means a whopping 87% of the power in the battery arrives at the wheels of the Model X. I also looked at some 2020 tests of the current generation of Model S. There's data reported by Car and Driver and Sean Mitchell that suggests that the current Model S can have drivetrain losses of less than 10%, or a battery to wheel efficiency of greater than 90%. Furthermore, we also know that over the years, the efficiency of Teslas have continuously improved. And Car and Driver reports that the motor efficiency of the Model S has gone from about 80% on the early models to as high as 94% on the 2020 models. Because of this, it's pretty reasonable to assume that the Cybertruck drivetrain will be equivalent or better than the Model S and X drivetrains in terms of efficiency. But to be slightly conservative, I'll assume a drivetrain efficiency of 88% for the Cybertruck, or an EDT of 12% of EN. How about rolling resistance for the Cybertruck? The first thing you notice when you look at the Cybertruck's tires is how meaty they are. I mean, these things are really off-road type tires. Or more specifically, they appear to be Goodyear Wrangler MTR Kevlar tires. Yeah, the Goodyear logo is clearly visible on the sidewall of the tires, and when you compare the tread pattern to that of the Wrangler MTR tires, it pretty much matches perfectly. What is different is that the sidewall of the tire appears to have been custom made for the Cybertruck wheels, or actually the wheel covers, but there is this one shot by Motor Trend that clearly shows standard Wrangler MTR tires on the truck. So we know the tires, but this doesn't exactly help us knowing what the rolling resistance is. See, rolling resistance information is notoriously difficult to find, and it's even more true for tires that aren't really trying to be efficient, like these Goodyears. Furthermore, we don't know if Tesla's estimated Cybertruck range is using this tire or a tire with an improved rolling resistance. What I was able to find is that off-road tires typically reduce fuel mileage by around 3%. And so armed with this information, I conducted a drag and rolling resistance calculations on a full-size pickup truck. I assumed a highway fuel economy of 11.8 liters per 100 kilometers, which converts to an EN of 374,016 kilojoules per 100 kilometers. I used a drag coefficient of 0.4, which is slightly greater than that for a Ram 1500 and probably close to that of a Ford F-150. I used a frontal area of 3.34 square meters, and that's pretty much exactly that of a Ford F-150. I used a vehicle weight of 2,100 kilograms, which is nearly equivalent to that of the lightest four-wheel drive Super Cab F-150 with a 2-meter bed. And then I finally used our rolling resistance coefficient equation for a 2.4 bar tire on a vehicle traveling at the average EPA highway test speed of 77.7 kilometers per hour. And this resulted in a rolling resistance coefficient of 0.012. Plugging in all these numbers, we find a drag energy of 37,405 kilojoules per 100 kilometers, a rolling resistance energy of 23,734 kilojoules per 100 kilometers, and a drivetrain energy loss of 312,877 kilojoules per 100 kilometers. These were the numbers for the street tires, the low rolling resistance, but I needed to find the rolling resistance coefficient that would increase energy consumption per kilometer by 3%. To do this, I held the drivetrain energy loss and drag energy constant while varying the rolling resistance coefficient. And then I slowly increased the rolling resistance coefficient until the sum of the rolling resistance energy, the drag energy, and the drivetrain loss was 3% above the original energy consumption. And finally, after all this math, I found an off-road tire rolling resistance coefficient of 0.017. That was a long one, but if you're still with me, let's jump back to the Cybertruck. We know that the rolling resistance energy is the weight of the truck multiplied by the rolling resistance coefficient. But what is the weight of the Cybertruck? Well, Elon actually mentioned this during the reveal.
The functionality I'm going to describe is within a space that is less than the most popular pickup truck in the United States, the F-150. So we didn't cheat in either width, height, or length. And we're able to achieve much greater capability in the same dimensions, same weight.
As was pointed out by Warren Redlich, the Ford F-150, which most closely matches the Cybertruck's dimensions, is the four-wheel drive super cab with a 6.5-foot bed. And according to Ford, the heaviest version of this truck weighs in at 2,362 kilograms. So I'm going to assume that this 2,362 kilograms is the upper weight limit of the Cybertruck. And interestingly, for reference, this is lighter than all of the current variants of the Model X. So this raises a question. How is Tesla able to keep the Cybertruck lighter than a dinosaur-powered truck without a battery and a Model X? Well, we got a hint back at the Battery Day event in September when Elon and Drew showed off their new 4680 cells, along with a new battery pack design that would form the central lower structural member of a vehicle. The changes they introduced will reduce vehicle weight in several key ways. First, by enlarging the cell diameter, it reduces the number of cells, which reduces the number of cell housing, which reduces the weight of the battery pack. And then second, they introduced this structural battery, which can form the central lower portion of the Cybertruck frame, which means you can remove a part of the frame, which would save some additional weight. And then finally, the Cybertruck's constructed with its body as the frame, the exoskeleton as they call it. See, most trucks have a body that sits on the frame, and I'm sure you can see how having one structure serving two purposes saves weight. So let's take our estimated weight of 2,362 kilograms and multiply it by the acceleration due to gravity and our estimated rolling resistance coefficient of 0.017. Multiplying by our 100-kilometer distance, we find a rolling resistance energy of 39,391 kilojoules per 100 kilometers. Okay, we are nearly done, and the drag energy is actually an easy one. Elon suggested that the Cybertruck could potentially hit a drag coefficient as low as 0.3. If you remember, this is quite a bit better than my Crosstrek and better than the Ferrari F40. To calculate the frontal area, I used my rectangles and triangle method, and I found a total frontal area for the Cybertruck of 2.86 square meters. I calculated air density at 70 degrees Fahrenheit, and I used the average EPA highway test speed of 77.7 kilometers per hour. When I multiplied everything together, we get a total drag energy of 23,981 kilojoules per 100 kilometers. When we put all the pieces together in our energy balance equation, we see that the only unknowns here is En, and we can rearrange and solve this equation using some simple algebra. When we do this, we find an energy in value of 72,014 kilojoules per 100 kilometers. To put this in a more common term, we find an energy consumption value of 0.20 kilowatt hours per kilometer or 0.32 kilowatt hours per mile. This really is a remarkable efficiency for an electric vehicle. And if we go back to the data that I mentioned from Bjorn, he was seeing numbers between 0.177 and 0.229 kilowatt hours per kilometer for a Model X. But we must also remember how dependent this number is on the speed we use when calculating drag. To better understand the impact of speed, I ran these calculations for speeds between 50 and 130 kilometers per hour. And then, as engineers like to do, I plotted the results as a curve. On the y-axis of this plot, we have the kilowatt hours per kilometer, and then on the x-axis, we have speed. And what we see here is that at typical highway speeds of greater than 100 kilometers per hour, the Cybertruck will likely burn through at least 0.25 kilowatt hours per kilometer. And it approaches 0.35 kilowatt hours per kilometer at speeds greater than 130 kilometers per hour. Now, this is for the off-road tires though, and if we add a curve for more typical on-road tires, you can see the energy consumption is improved at all the speeds as we would expect. And taken together, these two curves represent a good upper and lower bound on the probable energy consumption of the Cybertruck. So what does this tell us about the battery size of the Cybertruck? Well, we know that Tesla plans on offering 3 different Cybertrucks: a single, a dual, and a tri-motor. The single motor has a range of at least 400 kilometers, the dual motor is 480 kilometers plus, and the tri-motor has a range of 800 kilometers or greater. Instead of picking a speed, I decided to calculate the battery pack size using the En curves I just presented. For each data point, I multiplied the range by En, which gives me the kilowatt hours required to cover the distance. Obviously, this chart gives us quite the range of battery sizes for each model of Cybertruck. My guess is that the battery will likely be sized to hit the target range at about 100 kilometers per hour speed, and this ends up being consistent with some of the current Tesla vehicles. If this is the case, the single motor truck will have a battery pack size of about 100 kilowatt hours. The dual motor truck comes in at 120 kilowatt hours, and the tri-motor falls almost exactly on the 200 kilowatt hour mark. However, these results are for the off-road tires, and if Tesla goes with more road-oriented tires, you could expect these numbers to fall to about 84 kilowatt hours for the single motor, 100 kilowatt hours for the dual, and 168 kilowatt hours for the tri-motor. Now, I could be totally off on all these numbers, but I thought this was an interesting exercise, and I really learned a lot about vehicle efficiency, and hopefully my ramblings made some sense to you too. For all of you repeat viewers, thank you so much for all your encouraging comments. And I just wanted to let you know that I have lots more content lined up, and I'm also working on some new things for the channel for next year, as well as ways to increase the amount of content I can put out. So stay tuned for details on all that. I'm Josh, this is Next Garage, and I will see you in the next one.